Okay, hi everyone. Today we're going to work over linearization. And the idea is that we are making a curve thing into a line thing. Okay, a curve thing into a line thing. Because lines are easy to work with. Curves are not easy to work with. Lines are easy to work with. Curves are not easy to work with. And my easiest version is this. How can I find the approximation? What if I ask you guys to find f of x is equal to x squared, okay? But instead, find what is f of 1. How hard is f of 1? That's pretty easy, right? We know what that is. But what about f of 1.1? What would that be? Well, in this case, it wouldn't be terribly hard. I would just go 1.1 times 1.1. I'm smart enough to know that's 11 times 11, which is 121 with two decimals, 1.21. Okay, easy question, of course, because it's a square. But if I change this to a square root problem, good luck. So my point is that we're going to use this skill today to find out what that we could approximate the answer without getting too technical, without actually doing fancy crazy math. Because here's the idea. Let's go ahead and graph this graph here. X squared. I'm going to make it really zoomed in, okay? Really zoomed in, super zoomed in, super zoomed in, super zoomed in, okay? And if this is 1 here, okay, call this 1, 1, right? Okay, this is 1 and 1, right? Isn't 1.1 kind of like right next to it? So 1.1 would be like right there. But if I didn't know this trick here, or what if this was a square root of 1 versus the square root of 1.1? This would be a lot harder, and I would need a calculator to do this. So here's our trick instead. We know what the value at f of 1 is. Easy, that's 1. And what I'm going to do, instead of following this stupid curve, I'm going to instead just draw a line. Okay, when I draw this line here, how hard is it for me to generally write an equation of a line? And can anyone tell me what this line kind of looks like? In calculus, we've been talking about this line,
The tangent line?
the tangent line. Is it hard for us to come up with a tangent line so far? Not terribly. Guess what? This tangent line approximates our actual value of the graph. Now, if you look at my 2 points here, I'm going to color in slightly different colors. The tangent line is pretty darn close to the actual graph when x isn't too far away, right? They're actually pretty darn close. And we're going to say this approximation is good enough for our first start. Now, advanced calculus, what happens is you actually just draw a bunch of tangent lines and you get yourself really darn close to that graph. So with a couple of approximations, we can be pretty darn close within a bunch of decimal points of error. Okay. So here's our goal. We are going to 1, find the actual point. 2, create a derivative that gets us really close to that point, and then we're just going to plug in that value next to it. So here's our crazy part today. Okay. Let me get there. Okay. So here's what we're going to do. Let's go ahead and first find out what the derivative is. How hard is the derivative for this problem? Hard or not hard? You tell me, right?
Not hard.
Not hard at all, right? And our point is that these derivatives are not super hard. So we're going to say that the derivative here is just 2x. Easy peasy. Okay. And what we're going to do here is we're going to say, hey, we're going to find out what the actual value is. And then we're just going to add a little bit of difference here. We're going to add a little bit of difference. So our goal is to, here's our definition of linearization, is that the linearized line here's our definition, okay? A linearized line is the actual value here is really close to a close value plus the derivative, so the slope at that close value with a little bit of change. Now let me explain to you this equation, what this really is. So this is an approximation of f of x. Okay? It's just an approximate value of what it should be, right? Our tangent line in red here is really close to our actual value, but it's going to cost us less work, hopefully in the long run. Okay? What is A? A is our easy point. Okay? A is our easy point. Oh, darn it. Oh no, I wrote that. A is our easy point. Okay? X is the actual point. Okay. So let's put this into practice, and we'll come back and talk about it. So to find the point, we're going to linearize 1.1 for our function f of x equals to x squared, okay? So this is what we're going to do. We're going to go ahead and try to estimate what this value would be, and we'll see how far we are away from our true answer of 1.21. So the first point is to go ahead and plug in the easy point. Remember the easy point for 1.1 is 1 plus 0.1. Our easy point is 1. That's our 1. And what is x? So what is f? It's just x squared. So we're just going to write 1 squared. Okay. Sorry, that's on the side. We're just following the rule. Plus the derivative of a. We said the derivative of a, derivative of f was 2x. So we're going to plug in f prime at 1. How hard was the derivative at 1? Okay. Why are we using at 1 and not 1.1? Because our whole point is that we want to use easy points. The tangent line will rest at 1 and it'll deliver us to 1.1. Well, this is a slope, isn't it? Isn't that just a change? Well, if you guys remember, isn't slope another way of saying rise over run? Right? That's rise over run. And is x minus a, is that a rise or a run? That's an x change, isn't it? So if I multiply this by a run, doesn't that just give me a change in y, my rise? So here's the idea here. We have our easy y value. That's our easy. So let me draw some arrow. This is my easy y value. Okay, that's my easy y value. Then we're going to multiply our slope by our difference between our 1.1 minus 1. Okay, this is our actual minus our easy. And that gives us our difference, our change in x. How far have you left the slope? Oh, so how much have you run on the slope? And that will give you some type of rise. So change in y. So our easy y point plus our change in y gives us our approximation. So jumping over here, I'm sorry, it's kind of messy here, but that's 1 plus, what's the derivative? We said it's going to be 2x, right? So 2x times 1, so this is going to be 2 times 1 is just 2. What is the difference from our easy point to our actual point? Those very small. We only went a little bit, tiny step, that's 0.1. That's 1 plus 0.2 is equal to 1.2. This is our approximation. Now, I want to ask you this. Is our approximation pretty darn close to our actual equation over here? Our actual value? Close enough, right? And you might say, Mr. Ko, why couldn't we just multiply 1.1 times 1.1? Sure. But what if this equation was bigger? What if I wrote instead x squared plus 6x plus 8 at 1.1? This would be a little bit more work, wouldn't it? So let's actually use this example here real quick. Okay. And see where that takes us. Okay. So our function here is going to be f of x is equal to x squared plus 6, something a little harder. And I want you guys to approximate f at 1.1. And essentially, we are going to use linearization at 1.1. Okay, so 1.1 would be a harder value. Instead, that's use what value? Use 1, right? Wouldn't 1 be easy? So I'm going to use, what is f at 1? Well, f at 1, 1. 14 plus 1 is 15. That's 15, sure. We got that part. And then linearization for us is we are going to say it's f of a plus f prime of a, and then the difference of x minus a. Okay, again, that's just the difference. So what's the derivative? F prime is pretty easy. It's going to be 2x plus 6. What is f prime of a? What's f prime of 1? That's going to be 8, right? Pretty fast. All right. So my f of a, what is my approximate easy value? We know it's going to be easily close to 15. Now, what's a little bit of change that we have to add? Well, the derivative says, hey, it's changing at 8. But how far are you away? Are you a big leap away? We said, what's the difference between 1.1 and 1? That's just 0.1 away. That's not very far away. Our approximation is 15.8. Now I'm going to take out my calculator quickly, and I'm going to plug this in to see how close we are to the actual value. And hopefully I didn't mess up on math anywhere, because you know that happens. 1.1 squared plus 6 times 1.1 plus 8. The actual answer is 15.81. This is the actual f of 1.1. Are we pretty darn close? You guys believe it, right? It's not bad. And again, you might say, why the hell would we do that when we could just plug in 1.1? And this idea is that we're trying to find the approximation to things when actually doing the calculation would actually cause us more work. This is just a rough enough guess to say, hey, what do you want for dinner? Chinese food. Okay? For you to actually pick out a menu, have you guys ever said Chinese food and then it takes you another 20 minutes to figure out which items on the stupid menu that you wanted? This is the rough estimate. We're just having Chinese tonight. Okay? And it's good enough. Let's just get out of the house. At least let's get in the car and start driving. All right, so now let's show you guys doing this with a square root problem. The square root of 1.1, okay? That's my question. What is this approximation? So you have to break this problem up now. So we have to say that first the f of x is going to be square root of x, right? To make this a little easier for us, square root of x. Now, what's your real value? My x value is 1.1. But what's my approximate value? What's the easy square root that we do know? The easy square root that we do know is 1. Okay. Now, what if this question was instead, what's the square root of 26? What's your easy, okay, your x is 26, sure, right? But what's your easy value? What's the easy square root that you do know already?
25.
25, perfect. Right? And that's our value that we're going to use for A. Here's something kind of dumb.
Mr. Coe,
Yes, go ahead.
what's an easy value again?
An easy value is a value that you know how to solve without a calculator. Like the square root of 26, I don't know, but the square root of 25, I do know. Let's look at this as logs, stupid logs. Do you guys know what the log of 1.1 is? Nope. But do you guys know what the log of 1 is? It's 0, guys, if you forgot. Anything to the 0 power, anything to the 0 power is 1. So we do know what the log of 1 is, but we don't know what the log of 1.1 is. So you would say x is 1.1, but a is not 0.1. A is 1, because that's the easy log I know. We can actually do this problem to find out what the log of 1.1 is. Okay. Okay, so let me go ahead and finish this. So let's go ahead and use our linearization idea. Okay, so let's look at the idea again, repeating the idea. So whenever you have a curve, okay, whatever the curve is, this is not the right curve. Whenever you have a curve, the easy point, this is my easy value like we mentioned before. That is my f of easy. This is my easy point. And then we make a tangent line. We find the tangent line, which is the slope. And we just find the point on our tangent line. That's our change in x. And that gives us our y. We're getting really close with that tangent line. So we need our slope at our easy point, and we're going to subtract our little change in x here. Why? Because when I multiply a little change in x by slope, that gives me a change in y. Let me show you that again. F prime of a, that's really rise over run. That's a basic premise of it. And if I multiply this by a run, right, this gives me a rise. That tells me how much I've changed in the y direction. Okay, so I'm just giving you a little bit of change left. Okay, so my approximation of 1.1 here is, what's my easy point? It's just f at 1. And what's f at 1? That's going to be 1. Everyone go with that? That's just the square root of 1. I'll write it out. And the square root of 1 is 1. Yeah, easy peasy. Now, what's the derivative of square root of 1? That's a little harder. F prime of x is 1 over 2 square root of x. Does that go with you guys pretty fast? 1 over 2 square root of x. We're going to plug in f of 1 here, right? That's our easy value. We only want to take the derivative of the easy value. That's going to be 1 over 2 square root of 1, which becomes 1 over 2. Hey, that's an easy value for me. I like that. No calculator work here, because we knew what the square root of 1 is. And then x minus a, which is 1.1 minus 1, because this is my actual and my easy, right? And this, darn it. And wait, that's not bad. That's just 0.1, because we don't want to be too far away from our actual easy point, because the farther away, the more error you get. In this case, 1.1 is 0.5. 0.5 by times 0.1 is 0.05. 1.05. Now I'm going to take my calculator here to see how close we are. 1.1 square root of that is the actual value. F at 1.1 is, drum roll please, 1.488. Pretty darn close. Close enough? Yeah, close enough, right, for what it's worth, right? So this is the idea of linearization. It is not actually a hard topic, but it is us applying what we have been working with.
But Mr. Ko, the questions we're going to get on the homework are going to be like way harder than this, right?
You know, reality sucks, yeah. Well, actually, it won't be that terribly hard, but let's go ahead and take a look at one more rule here before we jump into the homework, okay? So the rule is, this is a approximation of binomial powers. So here is when it comes to binomials, okay? Binomials. Special rule. This is a special rule for binomials, okay? So here's the rule. If I said 1 plus x to the k, all right? So this is another rule for approximating. This is approximately simply just 1 plus kx. So if I'm trying to approximate this, careful, this is 1 plus. This isn't like 5 plus. This is 1 plus, okay? 1 plus. So
if the number in the parentheses was a different number,
and this doesn't work. It has to be 1 plus. It has to be super easy, because it's going to be 1 plus some decimal or so, 1 plus some value, okay? Right? So if I give you guys, for instance, okay, this is the book's example. It's pretty good. What if I write the cube root of 1 minus x? Could I change this approximation? This is really 1 minus x to the 1/3 power. How do you guys feel about that? Not too terribly bad? And then I'm going to actually change one more thing, because the book did a good job at this. It's going to rewrite this part instead of 1 minus, remember this has to be a plus, that has to be plus, right? This has to be plus. So I'm going to change this to a plus minus with a parentheses, just so that we're cool with that plus sign. This is the same as just me writing 1 plus 1/3, because that was my k value, times negative x. And this will give me a good enough approximation. What if I give you a problem that looks like 1 over 1 minus x? This can be rewritten as 1 minus x to the negative 1 power. So maybe I want you guys to see if you guys can give a pretty good guess to what the approximation would be. I'll write this in the minus, okay, to help you guys out. According to this rule, what would my approximation be? 1 plus is this what you wrote? Okay, let's give you guys another one. Square root of 1 minus 5x to the fourth. Okay, rewrite it so it fits this model. Rewrite it careful so it fits this model. Oh, so that's a plus. This is a plus. I'm sorry, that's a plus. It could have been a minus, not a big deal, but fit the model. The model is, I need a k on top. I need a 1 minus some, 1 plus some variable. I remember learning this in college, and I was like, what the crap? Like, wait, this is so confusing. Like, what? Do I really just write the k value and then I just copy what's behind? Answer is, yeah, this is all you do. This is just an approximation, right? This isn't the actual derivative, this is the actual value. But if I'm asked for an approximation, this is a good trick. Let's do one more. These are in the book. These are good ones. Okay, we got to write it like the model. The model is negative 1/2. Careful about that. The model is negative 1/2. Now, what are you going to write inside that parentheses? Okay, 1 plus negative x squared. You guys cool with that? That's your model.
What happened to the one that's in the square
In the
root?
root, yeah.
The one on top?
No, in the
No,
square
the
root.
one inside the square root.
This one here?
Yeah.
That's this guy here.
So we don't put the one on the top.
No, because I have a negative exponent.
Alright.
Huzzah. Remember that negative exponent is what flips it to the bottom. And then if I want to rewrite the model, is 1 plus negative 1/2 times negative x squared. Okay. All right. Let me pause here. Okay, just to go back to linearization. So let's say example, you want to take the square root of 65, okay? We know this is 8 point something, okay? 8 point what? So if we're doing linearization, the idea is we're taking f of a plus the derivative at a, and with a little bit of change. Right? That's our formula. So this is the idea. This is my easy point. And what's easier than square root of 64, right? That's the easiest thing in the world. And then we're going to find the change at 64. What is the derivative at 64? The derivative, so you have to come up with your function. We could take the derivative of that function. So this will be 1 over 2 square root of 64, which is not hard either. And our value is going to be x minus a. So that's going to be 65 minus 64. Okay, right? Because 65 is our actual versus our easy model. Why did I choose 64? Is because it's really close to 65, and I do know what the square root of 64 is.
Should the 1 over 2 root 64 be in parentheses?
1 over 2 root 64. 1 over 2. You could, but when I'm multiplying, it doesn't matter because it's just a fraction.
Okay.
Could you pick easy values? Like, I guess not, it doesn't really work for this problem, but like how far away from the actual value can your easy values be?
Great question. The issue with this is that, let me go ahead and draw you this example here. Okay. If I pick a tangent line at 8, because the square root of, 64, that's 64. Square root of 64 is 8, right? We know that's 8, easy. Okay. If I draw a tangent line, pretty quickly, the value is going to be too far away and the error would be really high. So that's why you always want to pick the easiest value closest to the value that you're working with. So if I'm working with 65, here, square root of 65, I know square root of 64, easy. But you could say, Ms. I know the square root of 25, but 25 is way over here and your error is going to be huge. That's no longer an approximation. That's a straight up guess. Okay. And that's a great question. How close should we be? Close enough that there's actually a way, if you continue reading the chapter about finding the error, what your expected error is, how far would you expect the value to be away from it? And that's also a thing that we do in calculus. We figure out how bad is my prediction, pretty much. Yeah.
That actually brings up another question for me. When we're going back to the binomial thing, sorry.
Yep.
The higher the exponent, wouldn't that make it so the higher the exponent, the larger the margin of error is going to be? So like, if you're like 1 plus x to the 260th power, something crazy like that.
Yeah.
Because that's going to grow exponentially, whereas that's going to...
Right. So any slight fudge in x, and the idea is these approximations only work when the value is close to the value as possible. So that's why the second part of the chapter talks about the error analysis. And we don't go through, I'm not going to go through that because it's just a bunch of headache. But you could take a look at it yourself. And all these values, when they teach it, they always talk about the error. Like, how far away can you be to still expect to get a good answer? So yeah. But you're right. If the k value is huge, of course, every slight move in x, it would be a huge error, a huge change. You're right. That's right. Okay. Same thing for linearization. The farther you get away, your easy value better be close to your actual value. If not, your error is going to be very large. Okay. Oh, let's go ahead and finish this. This is kind of dumb. Let's go ahead and, so the square root of 64 plus 1 over 2. This is 1, right? 65 minus 64 is 1. So 1 over square root of 8. And so it'll be 8 plus 1 over 16. Now, you would need a calculator for this, 1 over 16, unless if you know what that is. I mean, you could try doing it, but I'm not going to do it. So like half is 0.5. 1/4 is 0.25. 1/8 is 0.125. And 1 over 16 is 0.0625. So 8.0625. Never mind, I actually ended up doing it. And the square root of 65 is actual value. And the calculator says 8.06225. 8 rounding up. That's pretty darn close, right? Now, again, this is just a basic principle. Okay, this is again just a basic principle, and as you go into calculus, if you do study math, you'll learn more techniques to feed off of this basic technique to get you an even more accurate number. Do you think NASA scientists are going to use this? No, they're not, right? But they will use more advanced methods of this base version to approximate values. Right? And that's kind of, if you guys ever watched shoot, what's that movie called? What's that movie with the astronaut women calculating all those values? I haven't bought the movie.
Hidden Figures?
Hidden Figures, right? Do you know
Yeah.
how they're called human calculators? Because they're doing math like this,
Yeah.
right? So this is like the baby version of what they're doing, okay? But these people had doctors and master's degrees, whatever, or I mean bachelor's degrees in math, and this is kind of the basic premise of what they did, which I think is kind of cool. All right.